Hello, everybody. Welcome on the Lights on Data show. Today we have an exciting topic: evolutionary optimization algorithms. How does that sound to you?
Woohoo!
Yes.
It
And we're
sounds
actually,
difficult to me.
yeah,
Thank you for asking.
it does. And we're actually also going to giving away a copy of Marcello's book. All you have to do is put hashtag Lights on Data in the comments, and you're going to be entered in the draw. And it's going to be a book on advanced algorithms and data structures. And I'm going to,
Mm.
bring that up later on as well. So please don't be shy. But
And we are
now
also
I'll
going to
let.
make sure that we're going to talk about the book. And sorry to interrupt you, George. I will have the pleasure of introducing our guest, Marcello La Rocca. Marcello is a senior software engineer at Tundra.com, where he works on a scalable backend for wholesale e commerce. In his career, he has contributed to large scale web applications and data pipelines at companies like Twitter, Microsoft, and Apple. He's the author of Advanced Algorithms and Data Structures and created the JS Graphs library and the neat sort adaptive sorting algorithm. His work and interests focus on graphs, optimization algorithms, genetic algorithms, machine learning, and quantum computing. When he's not in front of the screen, he loves spending time by the sea, reading, ideally also on the seashore, and playing pool. Welcome, Marcello.
Hi, thanks a lot for having me on the show.
It's very happy to have you, Marcello. I'm going to start as usual with a more personal question. I am curious, what do you love doing by the seashore besides reading? And my second question, I absolutely have to ask this, how good are you at pool?
Um, yeah, I grew up close to the sea in a
Mm.
city on the sea in Messina in Sicily, and so I like doing everything on the sea. Like everything is better on the seashore. Yeah, I used to love swimming. I used to swim like uh,
Like a shark
10
or like a
kilometers
dolphin?
per week, maybe, like on my best.
Wow.
Now, like a little bit better, also because I'm a bit further from the sea right now. And about pool, well, there is no consensus on that. No, kidding. I'm no pro. I just like playing. I always loved playing pool. At some point when I was working on Twitter, I was playing fairly regularly. Also, like we had a tournament in the office. Mm,
Nice.
Oh, wow,
Yeah,
that's nice. And
yeah.
tell me, what about pool makes you like it so much? So, or maybe what are you training at pool? Is it precision? Is it just because you enjoy it just for the sake of it? Is it, or is there something in particular that attracts you towards pool?
I guess precision is one of the things. Also, geometry. I love
Mm,
playing when
nice.
when you do the indirect shots using the size
Angle.
yeah, yeah, exactly. Yeah, that's nice.
I love it. I love it. May I ask the next question as well?
Please.
I we wanted to ask you, Marcello, about your story. So, looking at your profile and on different platforms, it says that you are a hashtag algorithm lover and a hashtag quantum enthusiast. And I love the fact that you put these words together. And I wanted to ask you, what is your story? So, how did you end up doing this?
Where do I start?
With the
No,
beginning, please.
so the day I was born, it was like a rainy day. No, not that. I guess a little bit like closer maybe to the present. I mean, it's probably an average, pretty average story. Well, maybe the peculiar thing is, I love working on as a developer, like programming, since I was in the school. Like I started really
Wow.
early because I had computers around at home. My father also was kind of working on computers. Um, But maybe the peculiar thing was that at some point I had started working for a government-owned company in Italy, and that's pretty much the job of a lifetime here. So like it's a safe, steady job that you can do like until you retire. And I was, I guess, one of the few cases that left this kind of a job to pursue a different career. Because I basically left it, and well, first I started a PhD and then I started working for Twitter because that was my dream in the end. That was what I wanted to do. And the connection with the algorithms and quantum computer, I mean, first, like both hashtags in a way are connected because the things are the thing I like most about quantum computing in general is quantum algorithms and the possibility to use quantum computers to run some of the NP complete or NPR algorithms on a quantum computer in a reasonable amount of time. If we get there, I hope so, in the next future. Yeah, and algorithms has always been my favorite part of computer science ever since I was in college.
So this is bringing us to the evolutionary optimization algorithms topic. What is that? What is an evolutionary optimization algorithm?
Uh-huh. Yes. So, okay. I think maybe I take a short step back for this and define first what's an optimization problem, and from there we go to what are these algorithms. So, an optimization problem is a kind of problem, and there is a quite vast category of this. It's one problem that is basically, well, solving this problem is solving an optimization problem is equivalent to finding the minimum of a particular function, a target function, usually called a cost function. Well, actually, you can define a cost function and find a minimum, or define a target function and perhaps look at the maximum of this function. But these are equivalent things. So in these cost functions, I like to see them as landscapes. And in the case of 2D, two variables functions, this is pretty much equivalent. So you can imagine a 2D, like a 3D landscape, where the two variables corresponds to the two directions in a plane, and then the cost of the function is the height or depth of mountains and valleys on this landscape. And to solve the optimization problem, or you have to find the minimum or maximum of this function. So you explore this landscape and find valleys and peaks. And of course, this also works in higher dimensional spaces, but it's less immediate to have a visualization for those. So that said, like we have this cost function and that we want to solve, that we want to explore, like find the minimum. We have different ways to do that, and you can go with random sampling. So just imagine landing in random points of the random areas of this landscape and checking the altitude, for example. And if you do this many times, chances are that you will find yourself in a good position. Like, suppose that, for simplicity, like to imagine it this more easily, we are looking for the highest peak. If you repeat this sampling many times, and you keep track of the altitude and the coordinates of the place, at some point you will find like a good point of view, like a place where you can see all the horizon basically, and you see no other places higher than that. But there are also more structured ways that relies less on luck and more on deduction and work to get to a better place. One is gradient descent, for example. And this is a technique that allows you to when you land on one of such points, when you explore one of these points, you
Hmm.
check not only the altitude but also how steep is your surroundings, and if you want to go to the highest place possible, you move a little bit in the direction with the highest steep. So that is likely to bring you to like um, higher place, the highest place possibly in the future. You have to imagine like that you are, exploring this landscape, but there is kind of a fog for it. Like you cannot see everything around you, so you can only take baby steps when you are like using gradient descent. And of course, there are also other techniques, and one of these is using evolutionary algorithms. We relies a little bit more on the random parts or on luck, but also have uses heuristics to go from one solution to the next, trying to improve your current solution at any step.
Hmm.
To give you examples of the possible optimization problems, one could be like problems on graphs, especially NP hard problems. One could be the maximum clock, for example, which you could use on a social network to find the maximal subgraph on the social graph, where all people in this subgraph are connected to each other. And of course, you would like to get the biggest possible subgraph with these characteristics. And other examples could be more related to machine learning. For example, uh, um, linear regression in general, supervised learning can be seen as an optimization problem, and that's where gradient descent is useful. Or, for example, also to train a linear network. But as said, like gradient descent is not a must. You can use an evolutionary algorithm actually to learn, to improve, to find a better place in your landscape. And
So, hearing evolutionary makes me think of nature and
yes,
getting some inspiration out of that. Is there some sort of connection to that? It keeps on evolving.
yes, it is like there is one. I mean, there are different types of evolutionary algorithms. The idea behind it is that they are inspired by nature, and in particular by mechanisms of evolution. You have genetic algorithms. You have also refinements of genetic algorithms like memetic algorithms or artificial immune systems. I particularly worked on genetic algorithms or memetic algorithms since I was in college, and in particular, my master thesis was on a genetic algorithm in the domain of graphs, graph embeddings in particular.
Hmm. Are there specific steps that are part of an evolutionary algorithm that one should always take?
I mean, you can follow some guidelines, like it's sort of a template when you want to when you want to use such an algorithm. Like in general, for evolutionary algorithm, the idea is that you have a population that is the attempted solution, like at any step, and you want to evolve this population towards better solutions.
Hmm.
And with respect, for example, to other optimization algorithms, like randomized optimization algorithms, like simulated annealing, that is also inspired in a way by nature, but differently, not biology. Simulated annealing, for example, is inspired by metallurgy, the way that like metals um, are treated and processed. So with respect to simulated annealing, for example, the advantage of genetic algorithms is to have these pools of solutions, like keeping a better memory of past solutions through this population. And there are mechanisms, of course, that are used to ensure that a trace of um, non-optimal solutions at every step are um, are brought into the next generations. Like you see, for with simulated annealing, you have only one solution that you keep track of at all times. You may, remember the best solution you have found so far for optimization purposes, but you are like evolving one single solution, so one single point.
Mm-hmm.
And if you move at any point from a path that would lead you to the global optimum solution to a path that is at the moment seems better, but won't lead you to the best or always best ever solution. For like cities, like you are moving from one mountain to another in our landscape, and you don't see the top because there is fog, and you have a chance like a rope bridge from one mountain to the other, and you have a chance to move a little bit higher to the other mountain, right? And you say, okay, I will take the path because I get an improvement, but at the same time you don't know if you can go back to the other
Mm-hmm.
mountain later. Instead, in genetic algorithms, you keep track of the other path, of the old path, well, with a probability that is larger, that grows with the quality of the old solution. And like real evolution, if an individual is not best in the flock, but has some good characteristics that can be used later by evolution to produce an even better specimen, it's these characteristics, are kept in the genome, and they can come out later if the context changes or uh, just like by forcing the evolution, like we do with these algorithms.
So Tanisha here is mentioning mutation in genetic algorithms. Would that be an application to maybe determine the types of mutations that would occur when you introduce a new subject into the mix?
So like mutation is one of the key operators for genetic algorithms in particular. Like you have, say, two main operators. Well, we have a few operators, a few things that you have to do in a genetic algorithm. To say like a script you have to follow. You have this population, you force natural selection to, keep um, in a way force or encourage the best solutions to weigh more in the next iteration. You have
Mm-hmm.
crossover, which means combining two individuals to produce hopefully a better solution, and you have mutations. Mutations are fundamental in genetic algorithms because if we only used crossover, for example, we would never introduce new characteristics, new genes, um, other than the ones that we had in the first iteration of the genetic algorithm in the first population. Instead, mutations bring variability and accelerates convergence, but also makes sure that the convergence of the algorithm is not stuck, like the algorithm doesn't get stuck on a local minimum.
Mm-hmm. So I think maybe a couple of years ago or so, I saw this video, might have been from Google AI, and it showed this stick figure that couldn't really move. It was like very, very weird, and was trying to walk. And through trial and error, towards the end, it was like actually walking very similar to a human being. Would that be using an evolutionary optimization algorithm to be able to do that, to learn its way?
Well, they use, of course, reinforcement learning for that, and then using genetic algorithms or evolutionary algorithms is it's a possibility. think they use something more machine learning related
Got it.
for this.
Got it.
But actually, it is possible. For example, I wanted to quote a work from Dr. Professor Floriano and Mondada from EPFL in Switzerland. It's how I got closer to, like, I got interested in genetic algorithms. They were evolving small robots using, like, these robots had neural networks on them, and they had simple tasks like going to a goal or make sure they didn't go out of charge, like they were going to the charging station and their battery wouldn't go flat. And also they later introduced different robots like in a predator prey setting. Well, for these, for evolving these, and it was also before machine learning got so much hype, but they were using genetic algorithms and not like any kind of regression or
Okay.
it still was a reinforcement learning though. It was goal based.
So, what are some
Yeah.
other real life applications that we're seeing out there that's using this algorithm?
Yeah, and to there, I also wanted to say, are we doing anything regarding COVID with the help of this?
So for the last one, I honestly don't know if these evolutionary algorithms are used for anything about COVID. It's possible, like you can use them wherever you have to optimize something. Well, real life applications, again, like anything that needs optimization can use this, both on the learning side, on the learning, both on the learning side and also though if you have easy, real optimization problems like um, I don't know. Yeah, I mentioned the problems about graphs in the book. I also give an example about these genetic algorithm in the end used to solve a 0-1 knapsack problem that was given in a context of optimizing the goods that you are packing for an expedition to Mars. So any problem like the 0-1 knapsack problem is a like it's a famous computer science problem where you have a limited capacity on a knapsack or any container, for example, a crate that you send to Mars. And as you can imagine, if you are going to Mars, you cannot carry a lot of stuff because it would be a problem for the rocket to launch and to actually get there. So you have to use this capacity at best. And in the example I give, like you can have a limited capacity and you can bring goods like, I don't know, beans, potatoes, stuff that you can, like the astronauts could actually save and eat in time for as long as they have to stay there. And the catch is that you, in the 0-1 knapsack problem in general, or in this example in particular, like you cannot bring any quantity of goods, like you cannot choose 1 kilo or 1.5 kilos for potatoes, for
Hmm.
example, or tons probably in this case. You have to bring a full crate of beans or strawberry jam or whatever. So you can use an optimization algorithm like a genetic algorithm to solve this, and it gives you like suboptimal solutions sometimes, but it allows you to compute these solutions in a
That's
reasonable amount of time.
that's very interesting. Makes me think of The Martian, the book The Martian.
Yes, yeah. Yes, exactly. Yes, indeed.
So
And
so
sorry,
so
no,
we
just
we
want
can
to.
find, yeah, so and we can find this in your book as well, the advanced algorithms and data structures. And I'll put a link
Yes.
in the comments there on how people can get it, and they could actually get it for 35% off. So I'll share that link.
Yes, thank you. Indeed, like you can find it in the first chapter and in the last chapter of the book, and it should show you also should reflect the growth of the reader, like especially for newbies in the field of algorithms, and how you approach a problem differently when you have some experience and knowledge. Another cool application that I saw recently is using these evolutionary algorithms to calibrate the parameters of deep learning models. And there is a book that is a MIP that just started for Manning about evolutionary deep learning. It sounds really interesting. And
Hmm.
I'm looking forward to read more as the book is written, it gets written.
Awesome. We have a few questions coming in here. This one is
Yeah.
from Reza, so your name is not showing up, but he's wondering, do you think there is room to apply EAs in machine learning and especially deep learning? And if yes, in what area? Could you provide some examples?
Yeah, that's perfect. Like it's just what I was saying. It's evolutionary algorithms are perfect to make automatic the choice and the tuning of parameters. As you know, like when you train a model in machine learning, you have many hyperparameters, especially with deep learning that you have to tune. Well, besides you have parameters to, well, another parameter is the actual model that you can choose. But say that you went for neural networks or forests, random forests, then to tune these parameters in an automatic, semi-automatic way, like evolutionary algorithms are perfect. This is like the best and example that I can think of, actually.
And Christine was wondering, would some of the working natural algorithms be something like what Hachi is doing in the rainforest? So this company is working to create predictive algorithms of forest behavior to predict when threats like logging may occur by monitoring the forest activity.
I'm not entirely familiar. I'm not familiar with this work in particular, but from what I read, yes, I know that it's been used. That also random forests have been used for threat detections and intrusion detection. Yes.
And Tanisho is mentioning that NQueen's using genetic algorithms. I'm not sure if this means something to you.
Yes, the N queens is a classic computer science problem. Um, Yes, of course. Yeah, you can like find a suboptimal solution for this. Of course, the problem is hard to solve, so you cannot compute a deterministic solution in a reasonable amount of time as n grows,
Hmm.
because like it gets exponential in the size of the inputs in n. And this is perfect, like a perfect example where you could apply some heuristics and in particular evolutionary algorithms.
And can evolutionary algorithms be used in routing and logistics?
Um, in logistics, yeah, I know that it is like it is used. I you can also find some examples in this regarding logistics on my book. In routing, well, it's when you get to the hard problems connected to routing, of course. Anything in general, like heuristics and evolutionary algorithms, can be useful in any problem that is an NP hard or NP complete, any problem that for which a deterministic exact solution would take too much time to be computed.
Hmm. And sorry, another one here. How do you think to handle the computational efforts needed when applying EAs in deep learning?
Um, yeah, I'm not sure like what angle is this user asking about. I mean, there will, I guess, I mean, the if you talk about the learning, like the greatest effort is doing the training itself. And I don't know if there is an easy solution to this. I mean, you had the goal is, of course, using the least resources possible,
Hmm.
reducing the number of attempts that you do. One good ideas could be, for example, doing these evolutions or these fine tuning on restricted sets, and of course what you gain in resources, like what you save in resources. There is no free lunch. You'll pay it in the precision of the model, because of course if you train only on a smaller set, well, first you have to make sure that the set is big enough not to give you overfitting with these large models. But also it will be less precise than learning. The model will be less precise after learning on a smaller set rather than on the full set.
All right. I'm going to take another question here, but then we want to ask you a little bit about your book, if you don't mind. So, Raj is wondering if these algorithms can be used in conjunction with the IoT and the blockchain.
Well, depends on what's the goal. I I mean, I'll be honest, I don't know about any applications for these.
Hmm.
But if you can think of a problem where you can use some heuristics and some optimization, of course they can.
And are they better than simulated annealing or hill climbing in every aspect?
Um, so there is no global, like there is no overall winner. I would say it's more like it depends on what you have to do.
Hmm.
Simulated annealing struggles on some landscapes of the cost function, especially if there are many local minima. Genetic algorithms are a little bit better. Um, they have limits, of course, as well. One advantage was what I was talking about in the beginning, so that you keep somehow track of the past solutions and you can incorporate those in the next steps of the algorithms. While on simulated annealing, if you are unlucky in the beginning, you lose the path to the top and you might never go there again. Also, like there are another alternative is gradient descent, and it also has like some pros and some cons. Simulated annealing is very slow. Genetic algorithms are a bit faster, also thanks to mutations, but they have parameters that needs to be tuned, like for example the landing rate, or the for simulated annealing, how fast the temperature goes down, so how fast you learn. Gradient descent like it's faster, but it has some problems, like it gets stuck in local minima, and you need a differentiable function to apply it.
Got it. Thank you. Thank you so much,
I
Marcello.
just wanted to remind everyone that if you guys put in the comments hashtag lights on data, you have the chance of winning Marcello's book. And that being said, Marcello, can you talk a little bit about your book?
Yeah, thank you. I'd love to. Well, it's I took some time to write this. I started like some five years ago. It took like a lot of work. The idea for this book was to, create a bridge between textbooks and more like hands-on books. And so for almost all the chapters, what we do is trying to introduce a problem that the reader can clearly like see and imagine and see how some algorithms can be used to solve that problem. I also try to write these in a way that you can read the chapter, let's say in layers. Like you start, you understand the problem, you understand how you can study the problem and get to the solution, and then if you are interested, you can go into the details of the mathematics, for example, behind the problem and the solution, or the optimizing, maybe even how to profile and optimize your solutions. And uh, I think that's like something really important. I try to give good practices, or how some good practices could help you while you design an algorithm or go through a problem.
So you've really optimized the format of that book for the learning
For
of
sure.
the student.
Yeah, and I have to give credit to Manik also for that. It was actually a personal, personal growth, and a good experience for me to write this. I learned a lot about how there are good ways to teach to an audience and to make hopefully a subject like a topic interesting and more easily understandable for the audience.
Thank you. And Mike Nash was wondering, when you were writing the book, did you find that algorithms and techniques were updating while you wrote the book? And did you spend a lot of time researching all these things?
Well, yeah, luckily they still evolve. It's, I did spend like a lot of time researching. I tried to, for some problems, for example, my multi-dimensional nearest neighbor search, I tried to give cutting edge solutions. I try to include the like some material that is hard to find in any other book or even in around the internet, except for academic papers like
Hmm.
the similarity search trees, for example, or I try to go deep into clustering and use um, um, map map reduce version of clustering algorithms of even the famous one like k-means or other algorithms that are really hard to find like optics.
Got it.
Nice.
All right. I do want
Shall
to
we do the draw?
let people put in lights on the hashtag lights on data to enter the draw. So last chance to get in your entry before we're doing in here, and I'll put a comment as well where you can go ahead and purchase Marcello's book. But let's go ahead and do the draw here. Come on, come on, come on. Mike Nash,
Woohoo! Congratulations, Mike.
congratulations.
I hope you enjoy.
Yes, for sure.
Congratulations.
Mike was saying, I think it was him saying that he will listen to the episode again so that um he can grasp all the technical questions. So I think the book will come in very handy. So congratulations. And thank you very much for giving away a book, Marcella. That was kind and nice.
It's a
All right.
pleasure.
All right. Well, thank you so much for all the insights, and I feel like I've evolved a little bit during during this episode for sure by from your teaching. So thank you so much for being here with us.
Yes,
Thanks
and
so
thank you
much to
so much
you.
for
Sorry.
sharing these insights and for this is a very interesting topic. So thank you for agreeing to being here and for answering to all our questions. It was a pleasure to have you.
Thank you. It was a pleasure for me as well. Thanks so much for having me.
Thank you,
And thank you
everybody.
very much, as always, everyone. Very, very insightful questions as well. And have a beautiful weekend. And we'll see you next week.
Bye.